Welcome everyone. Thanks for coming for today's seminar. It is great pleasure that we have Dr. Susan Schorr from HCB. Professor Susan Schorr is the lead of Department Structure and Dynamic of Energy Material at HCB. She studied crystallography at the Helmholtz University Berlin. After her PhD in physics and HMI, I think now HCB, in Berlin, and Technical University Berlin, she did a postdoc and HMI and the Los Alamos National Laboratory in US. Then she moved to the University of Leipzig to do her habilitation, yeah, and became a frequent user of neutral scattering facilities in Germany, Switzerland, Great British, and France. Susan turned back to HMI, now HCB, to become the group leader in the Institute of Technology in the Solar Energy Division of HCB, continuing her research on material for solar energy conversion using neutral scattering methods. In 2008, she was appointed professor at the Freie University Berlin, where she taught crystallography, XRD, as well as neutral scattering. In 2013, it became a joint appointment between the Freie University and HCB. Thereby, she got the chance to build up a new department at HCB, which is now the Department Structure and Dynamic of Energy Material. Besides the research program, her department is responsible for the user service on several neutral difframeters, as well as at experimental section HCB's synchrotron source. Today she will give a talk with the title of Structural Disorder in Photovoltaic Absorber Materials. Let's welcome Professor Susan.
Yeah, thanks everybody for coming here. I hope you can hear me well. Thanks also to Professor Hau for giving me the possibility to show the research of my department here a little bit to you, a part of the research. So first I would like to introduce the Helmholtz Association, because we are called Helmholtz-Zentrum, so Helmholtz-Zentrum Berlin. So the Helmholtz Association is one of the largest research associations in Germany, and especially aiming for solving grand challenges the society is facing by conducting top-rate research in all different fields you can see here, and HZB is working in the field of energy. You see here a map of Germany with these 18 independent research centers, and the main point of the Helmholtz Association is that the center run a large-scale facility, which is also open to user service, and this makes it different, for instance, for Max Planck Society institutes. There are about 46,000 employees in all the 18 centers, and the annual budget of the Helmholtz Association is about 6 billion euros. And I come from that one, from HZB. And the large-scale facility we are running is the synchrotron radiation source facility, and this is called BESSY 2. So the energy research at HZB is mainly in these two divisions, the chemical energy division and the solar energy division. There is also more research than this, what I show here on the slides. There is also research on quantum materials. There is research for experiments with phonons at the synchrotron source, developing also the synchrotron source further. So this is just a part of the whole HZB's research. In the solar energy division, we work mainly on novel materials we try to find, and of course on halide perovskite solar cells. We also make tandems out of them, not my department, but HCB, other groups, tandem with silicon solar cells. So we have also the competence center for thin film technologies. This is mainly for silicon. And what is also very important are all the interfaces in the solar cell. So the interface in principle determines a lot the device properties. That's why we also take special care for interface and interface design at HSP. So, and my department is mainly working on this novel energy materials. I just show you some slides. So, what it's it's more from a commercial which was made for a fair in Germany. So we synthesized the photovoltaic absorber materials mainly in the form of powder, thin films, and single crystals, and we also use them because they are very well characterized later on as reference materials, which we'll send to our cooperation partners. So we do through advanced structural and optical characterization. And for the structural characterization, we also use large-scale facilities, so synchrotron X-rays or neutrons. So this picture is from my first PhD student I had, Christiane, and she's now full professor at the Martin Luther University in Halle in Germany as well. So we focus on semiconductors with non-toxic and abundant constituents, and of course long time stability, because this is an important property of an absorber, of a semiconductor, which will make it as an absorber in the solar cell. So we work on wide gap chalcogenides. Wide gap means up to 2.1 electron volt, so they can be used as top cells in tandem devices. We looked on ternary nitrides. Of course, we look on hybrid halide perovskites. Of course, they are not long-term stable, but maybe we can understand them better to improve stability. We also work on inorganic halide perovskites, on chalcogenide perovskites, and on chalcohalides. And as I said, we grow powder, single crystals, and polycrystalline thin films. My department is not making solar cells. We only make the materials and looking for the properties of the materials. Especially we look at defects, in particular point defects, because they have a big influence on the later on thin film solar cell efficiencies. We have also very good advanced analytics to study optoelectronic properties, and maybe you know Thomas Unold. He's also in my department, and he is a great expert in optoelectronic properties. So we can measure decay kinetics of charge carriers from TRPL. We can also do pump probe terahertz spectroscopy. We can do Kelvin probe, CV, or TRPL I already mentioned, and we do hyperspectral imaging to determine quasi-Fermi level splitting or maximum possible open circuit voltage. Since a few years, we have now a PLD system to grow materials libraries. That means we grow thin films with a chemical gradient. And using these materials libraries, we do combinatorial high throughput materials optimization, which is also very necessary to do to study novel materials. Of course, we educate young people. I teach at the Freie Universität in Berlin on bachelor and master level. I also teach a lot on international schools. Just last week, I taught in the UNSW HSPREE neutron training course not far from here in Lucas Heights at the UNSW is the Australian Nuclear Science and Technology Organization, and they run a multi-purpose reactor in Lucas Heights, and there are neutron scattering instruments, and I teach there in this course, and I also had beam time there. We also organize and teach X-ray diffraction school and the Rietveld school in our X-ray core lab. And of course, we supervise students. So this is the 4 groups in my department. We are about 27 people there. We have the crystallographic materials research, which Galina is the group leader. Then the combinatorial materials research and spectroscopy, where Thomas is the group leader. We also have a little group on correlative electron microscopy, where Daniel Aburas, maybe you also know his name, is the group leader there. And we run a number of end stations and beamlines at BESI. So we are also responsible for the user service at the synchrotron. And Daniel, my colleague Daniel, is the group leader of the diffraction and spectroscopy with synchrotron radiation group. We are mainly aiming to investigate structure property function relationships of compound semiconductors. And we also run the X-ray core lab, which is a central facility at HZB. So every PhD student or postdoc or scientist can come and use the diffractometers there for free without paying anything. And that's why we also organize the X-ray diffraction school and the Rietveld school for the PhD students who then will use the instrumentation in the X-ray core lab. So what I will show you today, I would like to give you an insight into structural disorder. So I think it's first important to clarify what I mean with structural disorder. You know, and you learn in your bachelor courses that a crystal is a three-dimensional periodic arrangement of atoms, ions, molecules, whatever, as it is shown here. And this is the unit cell we use to describe the smallest unit in the crystal. But in reality, it doesn't look that nice as here in the figure, because this is the ideal world. Each atom sits on its position. But in the real world, we have a lot of defects. And that's why this is sometimes also called the real structure of the material. So the defects we are working mainly on are point defects, which can be interstitials. So an atom is sitting somewhere in the crystal structure. We can have vacancies, as it is shown here, or we can have antisites. So when an atom sits on a position which is not the correct position. So and this point defects we study more in detail. And this I name here, this is the structural disorder I will talk about. So why it's important to study structural disorder? Yeah, especially in semiconductors. It's important because the defects inside the crystal structure, they determine the properties of the material. And of special importance are the point defects. And if we could manage the influence of these point defects to the properties, then we could increase the performance, and especially PV is mentioned here. So if you would like to manage their influence, we first have to understand them, their structural origin especially, and the concentration, and how this all depends on the chemical composition of the semiconductor. So we have seen that defects are really crucial for semiconductors. You know all from silicon. Silicon in principle is not conducting, but unless you have doped it. You have to dope silicon with phosphorus or boron to make silicon P or N type. With these compounds, semiconductors are shown here, so the chalcopyrides, copper, indium, gallium selenide or sulfide, or the kesterites, which is ZZTS, so copper zinc tin sulfide or selenide, or sometimes mixed with germanium. They are so-called intrinsic semiconductors. That means they are intrinsically doped by their point defects. So what that means, the point defects, they then, due to the point defects, we have levels, energy levels in the band gap. So this is the valence band and the conduction band, and in the band gap you can have levels. If it is closer to the valence band, then it's an acceptor level, and it's closer to the conduction band, then you have a donor level. And that's why the material becomes N-type or P-type conducting. So in this compound semiconductors shown here, chalcopyrides and kesterites, the dominant intrinsic defect which causes the P-type conductivity is said it's at the copper vacancies. And it's a shallow acceptor. That's fine. But the defects can also introduce deep levels in the band gap, not that shallow as I have shown here in the figure, deeper. And then this defect acts as recombination centers for the charge carriers. And so this is called the Shockley-Wright-Hall recombination. And this is something you don't want to have in your solar cell, because you would like that your charge carriers can reach your contacts and then that you have a current flowing. So that means if we have shallow defects, then we have shallow, low Shockley-Wright-Hall recombination rates, and these are the so-called good defects. And the deep defects is the defects you don't want to have, because they are detrimental for the absorber, and these are so-called bad defects. then normally you measure these defect levels by photoluminescence. That's fine, but just from the PL measurements you only know where are these levels in the band gap, but you don't know the defect producing that level. So that's why from PL you only get the energy level, but not the chemical and structural identification of the defect producing that level. So we do this by X-ray diffraction. We do the structural identification of the defect. Why we can do that? If we have enough defects, so if the concentration is high enough, and I mean it should be more than 10 to the 18 per cubic centimeter, which is a lot of defects, then the point defect will change the scattering cross-section of the structural site. So this means the cross-section on which the X-rays or the neutrons are being scattered. So this is describing the likelihood of the scattering on a structural site where normally an atom is sitting. So, and here I show you the atomic scattering factor shown here for copper plus, zinc 2 plus, and germanium 4 plus, and you will see it's very similar. And this is in principle the scattering power of these ions if you use X-ray diffraction. And you see the scattering power is very similar, so when you analyze your data later on and you would like to distinguish between copper and zinc and germanium, for instance, this will not work if you use X-ray diffraction. That's why we always use neutron diffraction to differentiate these isoelectronic elements, because here you see the neutron scattering length, B, and this is in principle what determines the scattering power of an element. And you see that it's very nicely different for copper and zinc. And that's why with all the materials we study here, we have electronic similar elements, and that's why we always use neutron diffraction. If we would not have this isoelectronic elements, we could use just X-ray diffraction to solve the problem. So, and for that we developed what we then called the average neutron scattering length analysis method, and I will just give you a brief introduction how we do that. This is just to show you the Kesterite type structure here. You see this tetrahedrally coordinated sulfur. In Kesterites always 2 copper, 1 tin, 1 zinc around here, and we have in the Kesterite structure 4 different cation sites. So this is the way the Kesterite structure is defined with the space group I4 bar and these 4 cation sites. This is not my idea to call them 2A, 2C. These are the Wyckoff positions, and if you remember, you maybe learned it a little bit in crystallography. Each space group has a number of Wyckoff positions which can be occupied by different atomic species. And for the Kesterite structure we have 2 positions for copper, the 2A position, which are the corners of the unit cell, and the middle one. The 2C position, which is this one and that one, as well as this one and the one which is here behind. Then we have the 2D position, which is occupied by zinc, and the 2B position, which is occupied by tin. And then we have all these defects which could be formed: antisites, vacancies, and interstitials. So now we do the neutron diffraction experiment, and we analyze the data as usual, done with powder diffraction data by Rietveld refinement. And one parameter you get out of the refinement is the so-called cation site occupancy factor. And this tells you if the site is fully occupied or not fully occupied, and it also tells you the scattering power of the site. So now we have the neutron scattering length, which is tabulated for, this is for example for these 4 different elements. And then, and this is our site occupancy factor we get from the refinement. And we use this site occupancy factor and multiply this with the neutron scattering length of the atom which should be on that site. So with neutron scatterings of copper for the 2A site. And then we get what we call the experimental average neutron scattering length, because this site occupancy factor determines the real scattering power of the site. So if there is only copper, then the site occupancy factor will be 1. If there is a copper vacancy, there is nothing to scatter, and then your site occupancy factor will be below 1. If there is zinc on copper, your site occupancy factor will be also below 1, because the neutron scattering length of zinc is smaller than this of copper. So that means the site occupancy factors will all differ from 1 because of the defects we have here. So this is the experimental side. Then we have to compare this somehow with the cation distribution we have on these 4 sites. So what we make is a cation distribution model. So we distribute our 4 cations on the 4 different sites, and from that we calculate an average neutron scattering length. So we take the assumed fraction of a cation on the Wyckoff position, J, and then we have to multiply this, of course, with the neutron scattering length of the cation, and then we get this calculated average neutron scattering length, which we then compare with the experimental one. And then we change the cation distribution model until we reach agreement as good as possible between the calculated average neutron scattering length and the experimental neutron scattering length. Now you may say, okay, you have 4 cations, 4 sites, couldn't you do that forever? That's why we have 2 additional requirements. We assume that each cation site is fully occupied by the different cations and the vacancies. And because we know what we have in our sample, we measure the chemical composition by wavelength dispersive spectroscopy, X-ray spectroscopy, grain by grain. So we know how many cation species we have, and we can only distribute what we have. We cannot distribute more, of course. So these 2 additional requirements also have to be fulfilled. So this is what we are doing mainly in the data analysis. We do the average neutron scattering length analysis with the prerequisite that we have to know the chemical composition very precisely and that our sample is homogeneous. That means if we have another phase, like another binary phase or ternary phase, this doesn't matter. But the quaternary main phase we study has to be homogeneous, otherwise it will not work. So we do the neutron diffraction and the Rietveld refinement. Then we calculate this experimental average neutron scattering length. These are the points here. And for each of the 4 sites, so 2A, 2C, 2D, 2B. And then we compare this with the neutron scattering length of the element. So that is for the red line is for copper, the blue line for zinc, and the black for tin. And you see already that the value for the 2A site, where normally copper is definitively below the copper line. And also the value for the 2C site is even more below the copper line. So these 2 points should be on the copper line because these are the copper sites. And this already shows you that you have not only copper on this position. Also the value for the zinc position, this one, should be on the blue line and it's lifted up. So this is the cation distribution model which fits best to the experimental data. This gives the stars. The stars is the calculated average neutron scattering length. And this is the cation distribution model we made for this sample here. So we have zinc on copper and zinc, this is zinc on copper antisites here, copper on zinc antisites, zinc on tin antisites, and copper vacancies. So now when the experimental and the calculated values agree, then we say, okay, this is our cation distribution. And from that we then know, now we know which type of defect we have. And because we also have the lattice parameters, we can also calculate the concentration for each defect per cubic centimeter. So it means we have a qualitative and a quantitative result from that. So now our experimental strategy is that we do a systematic investigation of these properties. So we synthesize the chalcogenides by solid state reaction from the elements in closed silica tubes, mainly below 1000 degree. Then we do a chemical analysis, so a part of the powder is embedded in epoxy, and then the surface is polished, and then we go to the electron microprobe analysis system and do the WDX spectroscopy. And the system is also calibrated, so we get real numbers. And the picture here is to show you just as an example, this gray parts here are the grains of copper zinc tin selenide, and the black part is just the epoxy where the grains are embedded. So then we do X-ray diffraction from all samples, also to check the quality of the material. And because we have these isoelectronic cations, we have then to add the neutron diffraction. If the sample has the quality of being homogeneous with respect to the quaternary phase. We get the structural parameters we want, so lattice parameters, and especially the site occupancy factors. From them we determine cation distribution and the point defect concentration. Of course, from each powder we grow, we also determine the band gap by UV vis spectroscopy. I think this is a method you're familiar with. So we measure diffuse reflectance and then apply the Kubelka-Munk pseudo-absorption function to make this tau plot, which is shown here. And then here from the slope here, you can then get the band gap value. So as examples, I would like to show you a few points, and I will start with the copper zinc disorder in the kesterite type materials, because this we studied a lot. In principle, the copper zinc disorder was discovered by neutron diffraction. So it was in principle the first sample series I synthesized 2005 in Leipzig at the university. I did the neutron diffraction. I did the Rietveld refinement. I made this analysis to compare the experimental and the calculated neutron scattering length. And I thought I would get a figure like that. So I have the 2 points for the copper side on the blue line, on the copper neutron scattering length, the tin on the tin neutron scattering length, and for the zinc side here. But what I got was something like that. And this puzzled me a lot in the beginning, because for the 2C side, the value was much lower than the neutron scattering length of copper, and for the zinc side, it was much higher. It was in principle on a level of half-half neutron scattering length of copper and zinc. And this was the first hint for the copper-zinc disorder. So we have zinc on copper and copper on zinc antisides. In principle, in these layers here, where we have the 2C and the 2D position. So here and here, or if you see it here and here. And since that, it was seen in all kesterite type materials, also in the sulfides, in the selenites, and also when we have germanium instead of tin. So the defect concentration of these antisides is 10 to the 20 to 10 to the 21 per cubic centimeter. That's why it's a lot. That's why we can see this so nicely. So then I also did experiments at the European synchrotron facility in Grenoble to study phase transitions, high temperature phase transitions in kesterites. And this is copper zinc tin sulfide, lattice parameter A and C half in dependence on temperature. And you see here this little step, which I could not interpret from the synchrotron data, because these are X-rays, so I could not distinguish between copper and zinc. And I just guessed in that publication that it's maybe a change in the cation distribution. Later on, this paper from Jonathan Scragg came out, and he asked me, "Oh, Susan, you have seen such a bump. Could that be maybe a change in the cation distribution?" I said, "Yeah, maybe, I don't know, it's synchrotron X-rays." What he did was he measured Raman spectroscopy, and then he compared the ratio of 2 Raman peaks, the 2A and the 3A peak, And he has seen that this, so he had samples he had annealed and quenched at a certain temperature, and then he could see this behavior, that this ratio changes. And so he speculated there is an disorder phase transition with respect to the copper zinc disorder at about 260 Kelvin degree C, for copper zinc tin sulfide. Based on that, later again, you see that from the years of the publications, we did a study on copper zinc tin selenide where we used anomalous synchrotron X-ray diffraction, and with anomalous diffraction you can then distinguish between copper and zinc, and so we had already defined the order parameter from that formula. This is the order parameter here over the temperature, and you see very nicely these are annealed at this certain temperature and quenched samples. How the order parameter is 0, that means you have disorder, full disorder, and then it increases, so the disorder gets less and less. But you see that we have not reached one. It will take almost forever to reach full order. And now we know what happens, and so we could interpret UV-Vis data from, for instance, here for copper zinc tin sulfide selenide, 3 different samples. The black curve is for S-Crown powder. Then the red curve is for quenched, that means very fast cooled powder. And the blue one is for slow cooled powder. And you see that the order parameter changes, so we have the highest disorder, of course, in the quenched sample and the lowest degree of disorder in the slow cooled sample. And with this, also the band gap changes. So it's the same material chemically, it's only the degree of copper zinc disorder changes, and with this changes the band gap. You can also see this in your PL measurements. So this is a series of samples from quenched to slow cooled, and you see a shift to higher energies in your maximum, in your PL max. So the PL max increases with decreasing disorder. And from all of that, now the people who make the solar cells tried to improve their efficiencies to decrease the degree of copper zinc disorder, and they developed an annealing procedure for the thin film. So they tried different annealing times and different temperatures, and then they measured the VOC, and then they decided, I think, for that one, because this has given the highest VOC of their copper zinc tin sulfide selenide solar cells. So you see from that there was also a technology development coming up. This is the so-called post-deposition treatment of the solar absorber. So you anneal it at temperatures below the transition, below the disorder transition temperature, and with this you can really then decrease the copper zinc disorder in your thin film. Is there also another way maybe to avoid copper zinc disorder besides this annealing? Yes, it is. And when you put some silver in your material, so here is some silver instead of a copper, a zinc tin selenide. This is the normal average neutral scattering length analysis. And now you see on the 2A position, you have the problem that now the value is not here, it's in principle on the line for zinc. And where normally the zinc is sitting, the value the value is up here at the copper value. So that means on the 2A side now we have zinc, and on the 2D side now we have the copper. That's another structure. This is a standard type structure where the divalent cation occupies the 2A position, and this layer here, where we had before the copper zinc disorder in the kesterite structure, is now the copper side. So 2C and 2D are not distinguished anymore in the standard type structure, and this layer is fully occupied by copper. And if we have some silver additional to copper, of course, also with the silver. And what we found is that, so it's this sample here, I show you, the one here. that we have a massive increase in the PL quantum yield if we introduce silver in the material. And we interpreted this in the way that because we have no copper zinc disorder anymore now, we have this increase here. Possibly this is the reason for it. So if you substitute copper by silver, you will change the crystal structure to the standard type structure, and there is no copper zinc disorder anymore. And we have a significant increase in the PL quantum yield. So from this disorder now going to the point defects, I would like to show you the off-stoichiometry in the Kesterite type materials. Well, this is a figure from an older paper from 2012, and it shows here two cation ratios. The copper over zinc plus tin ratio is here, and the zinc over tin ratio is here. Here is the stoichiometric composition. And the author of this paper summarized this here to show that the highest efficiency in Kesterite-based solar cells is a copper poor and a zinc-rich composition. Then we thought, okay, we have to look how off-stoichiometric we can make the material. How far we could go in the off-stoichiometry. We studied that. And then we also needed a model to describe this off-stoichiometric composition. And this was not our idea, it was the idea from Alain Lafont. He published it first, and he introduced the off-stoichiometry type model. And he called them by capital letters, A, B, C, D. And in this model, the chemical composition and the point defects are correlated to each other. And then we extended Alain's model to introduce more off-stoichiometry types, and now it goes up to L. And I will show you on the next slide what this off-stoichiometry type mean. So in principle, the Kesterite material can be seen in this quaternary phase diagram with copper, zinc, tin, and sulfur. And you could choose this plane here with a quasi-binary diagram, and we have here the copper, zinc, tin sulfide in the middle. So if we take this triangle out, and we have copper sulfide, zinc sulfide, and tin sulfide diagram with the Kesterite here in the middle. This would be the stoichiometric composition. But we know that the material can be, in principle, have all these four relations with respect to the cation ratios. It can be copper poor, zinc rich, copper poor, zinc poor, and so on. And this only works so nicely because the crystal structure is very, very flexible. It adopts all this point defects, so it can stabilize the point defects and be still, and the structure does not collapse. So we use the cation ratio plot always to show which off-stoichiometry relations we have. So this is copper over zinc plus tin and zinc over tin ratios, and here is the stoichiometric point. Now, where is, for instance, the A-type defect? So this is the line for the A-type off-stoichiometry. So the A-type from according to the off-stoichiometry model, to say that. And this is in principle the composition when you go along this line. And the A-type is correlated with copper vacancies and zinc on copper. And in principle now we have for each, this was here the A-type line. So each of these lines is one of this off-stoichiometry types. And it correlates then, each type correlates different point defects according to the chemical composition. So, and then you see in this area of this triangle here, in this area, you have copper vacancies, for instance. This is this stability region for copper vacancies. Now this is a model, and we had to prove that. And this is one example I would like to show you. It's copper, zinc, germanium selenide. And each point here is a powder sample. And this goes from AB type up to I type. So in principle, it covers this area in the phase triangle. And so that's why we expect all these defects I have shown here. So these are in principle the stability regions of these defects according to the off-stoichiometry type model. Okay, this is just one overview. This is the Catalan distribution, which then resulted from our neutron scattering length analysis. And so we start with this AB type sample going to BG, G, and then GF type and FI type. And you see, for instance, very nicely here, the copper zinc disorder between the 2C and 2D position. Also here between the 2C and 2D position, and also here. So despite which off-stoichiometry type you have and which point defects you can see, for instance, here, copper on tin, you always have copper zinc disorder. So now the question is there any sweet spot for the absorber composition? Here in each figure, I made for each point defect one figure, and each point here is a powder sample which was studied. So, and these are all the defects you don't want to have with the deep levels, so the bad defects, and these are copper vacancies and zinc on copper. These are shallow defects. So, and in principle, the favorable region with respect to the point defects is that one between the A and B type line. This is of course copper poor and zinc rich, but also if you are here, you are copper poor and zinc rich. But then you have more of the less favorable defects. So in this area you have mainly copper vacancies, zinc on copper and zinc on tin. These are the defects with the highest concentrations, and according to the calculations in that paper, copper vacancies are shallow, zinc on copper is also okay, and zinc on tin is, it's not too bad to say. It's not a mid-gap defect. So, and now this is in principle the basis for defect engineering. Now you can work on the composition of your thin film. You always have to keep in mind that in your thin film you will have compositional variations. And this is also something you should try to avoid, because if you have compositional variations, you have variations in the off-stoichiometry type, and with these variations in your point defect concentrations. And because of that, you will have bandgap fluctuations. Because this is shown here in copper zinc tin sulfide, if you go from A type to B type to G and F, and this is the bandgap, you see that the bandgap changes. And because of that, you will get electrostatic potential fluctuations, which then will decrease your open circuit voltage. To show you a real-world example, so this is a ZZTSE absorber. This was an absorber from Edgardo from Barcelona, and it was studied by NanoXRF at the European Synchrotron Radiation Facility. And you can see this is for copper, zinc, tin, and selenium, the cross-section and the composition distribution of these elements. And you can see that it's okay, it's already very good, but it's not homogeneous. For instance, if you measure the integral composition of your whole thin film by XRF, you will get this value and you will say, oh nice, I'm on the A-type line, great. But locally you have these compositions, for instance, and this is not very good. So that's why it's really important that you grow your absorber thin film as homogeneous as possible. So an optimization of the growth process towards chemical homogeneity is really important. One slide about the monograins, because monograins are little single crystals, and in principle the single crystal inside is homogeneous, and also in a batch it's very homogeneous. It could be also sometimes inhomogeneous when something went wrong in the growth process. They are grown in potassium flux, but they show a good homogeneity. And because it's like a powder, we can do our neutron diffraction experiments on that and determine the order parameter and the point defects. And then we can compare these values with the real device efficiency and the VOC and other parameters, because it's a working solar cell later on. This is just an overview of copper zinc tin sulfide selenide monograins with a sulfur content of 60%, where they are all in between the A and the B type line. So these are the cation ratio plots. And here is shown the order parameter. So green means less disorder. So we have less disorder here at that end and higher disorder when we go closer to the B type. These two figures are for the 3 point defects we have between the A and the B type. So copper vacancies, zinc on copper and zinc on tin. This is zinc on tin only. You see it's lower when you go closer to the A type line, of course. And this is the device efficiency. Of course, it's not great. It's 7.8%, so it's a normal batch for them. They have the record of 12 point something, I think, for the pure sulfide monograin solar cells. But you see that you get the highest efficiencies here in this corner, where you have the lowest copper zinc disorder and the lowest concentration of the zinc on tin point defect. So in this study, we could correlate very nicely the structural disorder with PV parameters. Then I would like to show you some work we have done on other quaternary chalcogenides, which are sometimes called Kesterite-derived materials or Kesterite-like materials. And then we have also other crystal structures we have to take into account. You have seen the Kesterite structure, this one, and I showed you the stannite structure, this one. But we also have Wurtz-stannite or Wurtz-Kesterite structure. What they have all in common is the basic building block. The basic building block is shown here. So this is this coordination tetrahedron with the sulfur in the middle and 2 copper, 1 tin and 1 zinc around. And this is in all 4 structures the same. It's just differently arranged. And if you go from stannite down towards Kesterite, you see that you go from 2 tetragonal space groups to an orthorhombic one and then even to a monoclinic structure. That means you have an increased distortion and tilting of the anion tetrahedra. Of course, silicon belongs to the same family, so this is the adamantine compound family, and in silicon you also have the tetrahedral coordination of silicon by silicon. But because silicon is cubic, the tetrahedra are not distorted and not tilted. But if you go down in symmetry, then you have an increase of distortion and tilting. It's like in the perovskites. So I showed you the copper zinc disorder, which is existing on these 2 planes here, between the copper side, the 2C side, and the D-valent side 2D. So when we now go to the stannite type structure, we have these copper planes here and also here. So within these planes, we will have we will have to exchange with another ion. For instance, we could exchange with this D-valent coming up to that position, and then we also would have a disorder. Now the question is if this happens in stannite type materials. And we studied this series where we have manganese instead of zinc. And then we mixed the cations, so we exchanged germanium and tin. And we also did an anion alloying sulfur and selenium. And the copper manganese tin selenide, sulfide selenide, and yeah, it's the same here. And the copper manganese tin sulfide, they crystallize in the stannite structure, and the other 2 with germanium crystallize in the Wurtz-stannite type structure. So that means we will have a structural change when we exchange the cations, and we will have no structural change when we exchange the anions. So the question was, if we have copper manganese disorder, that means do we see copper on manganese and manganese on copper antisites? This is just for the 4D side, which is the copper side, so this copper plane. For 3 different samples, and copper manganese tin selenide with different stoichiometries. These are the ratios here, 2 cation ratios. And you see this is not much manganese on copper we see in these 3 samples. Also in the sulfide, so this is a copper manganese tin sulfide of stoichiometric compound. There is also not much manganese on copper. Just to compare the situation with copper zinc tin sulfide, this is the amount of zinc on copper we get, and this is the copper zinc disorder. Here it's much less. It's less than 5% of the site is occupied by manganese on copper or copper on manganese. And that's why we call this not disorder, we call it swapping, because we found in another paper where it goes about a totally different material that they call this antisites with a fraction lower than 5%, they call it swapping. To distinguish when we have fractions much higher than 5%, this is disorder. And now in this series where we alloy cations and anions, we see this is the fraction. It's always, it's mainly below 5%. There is one exception if we mix copper manganese tin sulfide and copper manganese tin selenide. Then we have an increase of this copper on manganese, manganese on copper antisites. It can go up to 25%. So that's why we say that we have copper manganese swapping mainly in these mixed crystals, but also a little bit of copper manganese disorder, but only in the copper manganese tin sulfide selenide mixed crystals. What about the band gap range you can cover with this series? In principle, you can go from 0.9 electron volt up to, you mix and mix and mix, up to 2.1 electron volt. And then, of course, it goes down depending on which mixture you obtain. So in principle, these materials could work for a double junction or triple junction solar cell material. So you can cover a quite large band gap range. Now going away from the chalcogenides and show you a little bit about ternary nitrides we did. Why ternary nitrides? Yeah, we look for sustainable absorber materials, and the ternary nitrides are said that could be earth-abundant alternatives for 3,5 compound semiconductors. So 3,5 like aluminum nitride, gallium nitride, indium nitride, you know all that. And ternary nitrides like zinc silicon nitride or zinc germanium nitride, which is shown here, or zinc tin nitride, this is the band gap, they are possible materials also for solar cells. There is only there is a simulated device efficiency reported for zinc tin nitride, about 22%. But what was for us the most interesting with these materials is that you not only can tune the band gap by alloying what you normally do, but you also can tune the band gap by cation order or disorder in the material. And that's why we studied zinc germanium nitride to have a look if we can change the band gap by changing the cation disorder. Now, what means cation disorder in these materials? The zinc germanium nitride, as the other 3 nitrides, have 2 possible structures to crystallize in. One is the Wurtzite type structure, where you have only one cation side, the 2b side. So it means both cations are on that side. And of course, then you have disorder. If you have only one side, no chance to get order. The other possibility is this beta sodium ferrite type structure, which is also rhombic, where you have 2 cation sides. And this gives you the possibility that you have an ordered distribution of zinc and germanium. So you have a zinc side and a germanium side. Again, also these compound semiconductors are tetrahedrally coordinated, as we had before. Now we have to synthesize the material, and this was not so easy to synthesize zinc germanium nitride. We started with an oxide precursor, zinc germanium oxide, and then we did the ammonolysis reaction. So we reacted this with ammonia in a closed tube at a certain temperature and for a certain time. Then we did the chemical analysis by XRF spectroscopy to get the zinc and germanium values. And then we used something which we could do at the Technical University Berlin in the chemistry department. We did what they call hot gas extraction, and then we could determine nitrogen and oxygen content. And what we found, that we have always some oxygen in the material. So in principle, it's an oxynitride. We never could manage to get the oxygen out. This has some consequence. Then we do X-ray diffraction as usual. And then we have not only the problem that zinc and germanium are isoelectronic, but also nitrogen is a light element and has a very low X-ray scattering cross-section. And that's why, again, we need neutrons. And this is the neutron diffraction pattern, one of those we measured. This is the same, so this is in principle 4% of oxygen in the material. And again, we do UV spectroscopy to get the bandgap energy. But this is just an overview of some X-ray diffraction pattern, a part of the X-ray diffraction pattern of some of the zinc germanium nitride samples, where we have a changing zinc germanium ratio, what we get from the XRF measurement. And with this, the oxygen to nitrogen ratio changes. Because when the nitrogen, when we have more oxygen in here, we come to this zinc germanium ratios. So they correlate with each other. You see here for one of the temperatures for different reaction times, we can change the oxygen to nitrogen ratio, and with this changes the germanium, the zinc to germanium ratio. And we could already see from this XRD pattern that the oxygen-rich compounds crystallize in the wurtzite type and the oxygen-poor in the beta sodium fluoride type structure. Why we see this? Well, you see here this peak splitting. So this peak here splits to two peaks. This stays as one peak, and this splits also to two. This is an indication of changing this crystal structure. And in principle, it depends on the synthesis conditions, the temperature and the reaction time. Now, where are the cations? So we have two sides, as I said before, the zinc side and the germanium side. And this is again the site occupancy, so one is full. For two columns always belong to one sample. And this is for different oxygen contents. So this is a high oxygen content and this is a lower oxygen content. And this figure we would expect if you would have full cation order. So the zinc side would be occupied by zinc only, and the germanium side by all of the germanium, and a little bit of zinc because of the oxygen. We have a zinc to germanium ratio which is always larger than 1. But you can see here from the figures that on the zinc side there is always something green everywhere. So that means we have more a situation like that, that a part of the germanium is on the zinc side and a part of the zinc is on the germanium side, coming on top to the zinc on germanium andesite we have due to the off-stoichiometric composition. And this with the stars we call the intrinsic disorder. So the zinc germanium star and germanium on zinc star andesite defect is the disorder we are looking for. And now the question was if this depends on the oxygen content or not. So this is the germanium on zinc star andesite defect and the oxygen content here shown. And you see that, that's why I marked this blue here. We have here different, so each point is one sample. We have here different samples with almost the same oxygen content, but different amount of andesites, also shown here. And second, we could say there is somehow a limit for the intrinsic disorder. And this considerations brought us to the point that we need an order parameter because otherwise it's all crowded. So we defined our order parameter in the following way. We said, okay, we have these 2 points fully ordered or fully disordered. What means fully ordered? Fully ordered means that we have no a germanium on the zinc side. So no green here. Fully disordered means that the germanium on the zinc side is the same as the germanium on the germanium side. And with this, the first one, so that depends on, because the full germanium content depends on the oxygen content, but the defect, the anti-side defect, does not depend on the oxygen content, as we have seen before. So we had to bring these two things together. We want this fully ordered is 1 and the fully disordered is 0. So we defined it like that. This is the order parameter we defined. It's the germanium on zinc star anti-side intrinsic defect, and we have to divide by half of the germanium content. And then we got this figure. So each point is one sample. This is the reaction time, and the different colors are the reaction temperatures. And now we see that our points are nicely ordered if we look for the order parameter, which goes from 1, which is fully ordered, to 0, which is fully disordered. And now you can see that we can tune the disorder by choosing a certain couple of reaction temperature and reaction time. And this is in principle what we want to know, if this is possible. So now we know that we can tune the disorder by the reaction conditions. The question is, what has happened with the band gap? This is the band gap versus the oxygen content, and on the right side you see the band gap versus the order parameter. So here is the order parameter. You see that the band gap is influenced from both, from the oxygen content and from the disorder, the cation disorder, but somehow in a different way. If you look for this sample I marked with the star, this is the sample with almost no disorder. Here, almost, so this is the lowest disorder we have, but it's not the lowest oxygen content we have. So, and if we have fully disordered material, like here, then the band gap doesn't change anymore so much. In principle, then it's constant. Also, the open circles are disordered, zinc, germanium, nitride, and then you see that the oxygen content changes, but not the band gap anymore. So the last point I want to touch is the hybrid halide perovskite, just quickly. The question was, is there structural disorder in hybrid halide perovskites? Okay, hybrid halide perovskite are these amazing materials which are defect tolerant. But then people say, we can forget about structural disorder, defect tolerant material. So what means defect tolerance? Defect tolerance for a semiconductor means that the material keeps the properties despite the presence of defects. So this material has still in the solar cell the high conversion efficiency, even if it has a high concentration of point defects. So, and there are different things, different properties you can get defect tolerance. For instance, in the chalcopyrites, so copper, indium, gallium, selenide. We studied this intensively here in these papers, for instance. There are a lot of defects. In this 10 to the 20, 10 to the 21 per cubic centimeter. But the material makes a good solar cell. And there is the theory from Zunger, from Alex Zunger. He came up with that the defects are formed defect pairs. And so the energy level of the defect pair is then shifting to a shallow level. They are not in the middle of the band gap anymore. And with this, they are not harmful anymore. Second, of course, the point defects can be shallow. You only have shallow point defects, or you have point defects which are deep, but they have a low capture cross-section. And these 2 points are found valid for hybrid halide perovskites. And that's why that despite they may have a lot of point defects, they are not bad for the material. So hybrid metal halide perovskites, you know, you have these molecules in the material, methyl ammonium or from amidinium, for instance. What was mostly studied is methyl ammonium lead iodide, so MAPI. This is the composition of the record solar cell. It's cesium, methylammonium, formamidinium, lead, iodide, bromide. So it's a mixture of cations and anions. They all crystallize in the perovskite structure. So the perovskite structure is defined as a network of corner-sharing octahedra, as shown here. And if the structure is not cubic, they are tilted and distorted, like in these chalcogenides. But you have not only this static structure, what we looked before for all the other materials. Due to the organic cations, they also have what is called a dynamic structure. So these organic cations are large dipole moments in the material which are very flexible. So they can have different orientations, which this is what we call structural disorder, or they also can rotate. So they can make flips. And we studied this as well by quasi-elastic and inelastic neutron scattering. Just a few slides. So some materials adopt the cubic perovskite type structure like methylammonium lead bromide, where the molecule is completely disordered. It can become a tetragonal perovskite like MAPI, where we found 8 different orientations for the molecule, or it can be orthorhombic like methylammonium lead chloride, where we have only 2 orientations of the molecule. And MAPI shows the structural phase transitions. It goes above 330 Kelvin to cubic, and then it's at room temperature, it's tetragonal, and below 161, it's orthorhombic. So we studied the orientational disorder of the methylammonium molecule in methylammonium lead iodide. We combined synchrotron X-ray powder diffraction, this was done at Bessie, and neutron powder diffraction. And the space group we found for the perovskite structure is I4CM, so this is a non-centrosymmetric space group. The octahedra are tilted along the 001 direction, and we found 8 possible orientations of the molecule. So these are here the 8 different orientations, or here in the bulb, these 8 different orientations. That means we have an 8-fold disorder of the molecule in MAPI at room temperature. Why the space group is so important? There were a lot of publications saying that MAPI is ferroelectric, and that the ferroelectricity in MAPI is also a reason for the high efficiency, because it accelerates the charge carriers when they go through the material. Now, from the crystallographic point of view, only a material which has is non-centrosymmetric can show this property, because the centrosymmetric space groups have an inversion center. And materials with an inversion center cannot be piezoelectric and also not ferroelectric. This is just not possible. So far in literature, the space group was given as a I4/MCM, which is a centrosymmetric space group. If that would be true, MAPI can never be ferroelectric. So that's why we studied this not only with neutrons, as I have shown you before. We also went to the diamond light source in Great Britain to do anomalous diffraction at the lead edge to really prove that MAPI adopts the I4CM space group, which is non-centrosymmetric, and then, of course, it can be ferroelectric. I think I maybe will skip the, just one slide, and the next one I will skip. The rotational dynamics. What are the rotational dynamics? So this is the molecule, Ma molecule, for instance, methylammonium, and it can rotate around this axis, so it can rotate like that. Or there is a 3-fold rotation along the CN axis like that. So this is a measurement what we obtained at the Institut Laue-Langevin in Grenoble at the reactor source there. And this is called quasi-elastic or inelastic neutron scattering. Now here you see an energy scale. This is the scale who measures how much energy the neutron has transported to the sample during the measurement. And this sharp peak here, this is in principle the Bragg peak. So this is the elastic scattering where you have no energy change. And then you see here a broadening of this peak at higher temperatures, which then gets a little bit lower if you decrease. And if you decrease more, you also see the lattice vibrations coming up here. This is then the inelastic scattering, and you can measure also phonons with a neutron scattering. And from analyzing this broadening, this quasi-elastic broadening, you can get an information about, I will show it here, about the characteristic relaxation time of these jumps. This is, for instance, for the C3 jumps. These are the jumps along the nitrogen-oxygen axis. So in principle for MAPI, it's 1,635 picoseconds before it jumps to the next. And this decreases when you go to the pure chloride, and this is just with a little bit chloride. And you see that this decreases, and this is a hint that when you substitute chloride instead of iodine, this weakens the hydrogen bonds a lot. So the bonds between here the hydrogen in your molecule and the halide. And we studied this with chloride because when you remember when it starts with halide perovskite solar cells, they started with MAPI and then they put a lot of chloride in the thin film. That's why we studied a lot with the chlorides in the beginning. And then you can also get the activation energies out of that. So this is just what I want to show you today. I'm sorry, I'm a bit too long. So I want to show you that the intrinsic point defects are really important to study because they determine the electronic properties of the semiconductor. And it's also important to know their structural origin. Not only the levels, but also which defect you have. Because then you can do defect engineering to improve your power conversion efficiency of the solar cell. And we derived the structural disorder by careful analysis of diffraction data where we used X-rays and neutrons. I showed you the structural disorder in Kesterite-type solar cells, especially the copper-zinc disorder, vacancies, andesites, interstitials caused by off-stoichiometry. We have the off-stoichiometry type model for that now. And we also could show that the bandgap energy changes with the off-stoichiometry type. I showed you the disorder in the Kesterite-derived materials like copper, manganese, germanium, tin sulfide selenide, which have stannite type or Wurtz-stannite type structure, and they show the copper manganese swapping. That means these two andesite defects, copper on manganese, manganese on copper, are less than 5%. I showed you our studies on the ternary nitrides, where we could really show, which was speculated in literature before, that the zinc germanium disorder correlates really with the bandgap energy. And I showed you a little bit of our work on the hybrid halide perovskites. They are defect tolerant, but now you have an orientational disorder of the molecule, which is also important for the material. And I think it also leads to the weakening, to the low stability of the material because of these weak bonds and the weakening of the bonds you may have. So this is to thank all my colleagues from the department, especially Galina, Daniel and Joachim, and a bunch of PhD students, the instrument scientists for neutron diffraction, and the sources you see we measure everywhere we can get neutrons. So we also measured a lot in Australia. We measured the different synchrotrons. We get funding from different EU projects. And I thank you for your attention, and I added the announcement for the 15th Kesterite Plus workshop, which will be next year in Berlin. So we will organize it at HZB. It will be in June.
Thanks, Susan, for the nice talk. Very comprehensive of this structural disorder of the thin film materials. Do you have a question for the talk for Susan? Jialiang?
Thanks, Susan, for the nice seminar on the neutral diffraction analysis of Kesterite and other materials. Yeah, and I have one question about the neutral diffraction analysis. you mentioned that we can get the density, the defect level, and also the concentration of the density of different defect types, and we know that we also can get this kind of information from other categorizations like capacitant-based categorization like ASODLTS, and of course there are appearance of defects with the cluster compensation. Can you comment on there's any link between those two kind of measurement or any other information we get if we combine these two?
For the kesterites, we don't have that, but for the chalcopyrites, because there are these nice papers from Alex Zunger who calculated the defect levels in the chalcopyrites and also said which defect it should be. And because we have done the same work also on chalcopyrites, and with the help of these papers, we could then really say, okay, we have this material with these defects, and according to the paper from Alex Zunger, it should be that levels. Then we measured the PL, and we have seen these levels, and so we could correlate that. For kesterites, it's not so easy to get a good PL signal. They are very often quite low. So that's why we have this correlation for the chalcopyrites, but not for the kesterites measured. Yeah.
And one quick question. You said for the analysis, the uniformity is very important for the materials. So I just wonder, is there any spatial resolution or spatial dependent information we can get from the analysis of the neutral diffraction analysis? The problem is that we perform this really complex analysis only if we have homogeneous powder, and what we name homogeneous is that, so we measure in principle about 60 grains in one powder, and then we check the amount for each of the 4 elements we measure, or 5, and it should vary only within the experimental error. So this is 1%, I think, or 2 almost. So if it's out, then we say it's not homogeneous. The problem is then we have too much variation in the defects maybe, and then we cannot apply our average neutron scattering length analysis, because it makes no sense then anymore.
Hi, Susan. Very nice talk. I have 2 questions. The first one related to kesterite and maybe all the other like a compound inorganic semiconductor materials, and the second will be related to the perovskite. Mm-hmm. The first question would be like, for example, for the kesterite, we're showing here a lot of like a defect, right? Mm-hmm. But actually, in the last 2 years, there are a couple of like groups have already shown like the fabrication sequence, like the stack structure, and the later on annealing actually have a big impact on the disorder or defects we see, because we saw like we have a lower band gap. CZTS-SE have 15% efficiency. Our group actually also we have breakthrough on the high band gap, like a CZTS, pure sulfide CZTS. We got like beyond 13% already, certified one. And we see like how this different type of like a precursor structure and also the annealing impact on the defects. Mm-hmm. But here, like I think because of the limitation, can we only use a powder and a mono green layer? Yes. Yeah. So I just wonder like whether is there anything we can, for example, address like in the real defects in the thin film one in the future.
In principle, because of the off-stoichiometry type model, so if you know the composition, if you know the composition of your thin film, then I think what you measure is the XRF, and you get the integral composition of the whole film, which doesn't mean that this is the real composition of the kesterite. So it would be good if you could measure your composition more on a cross section,
to get an idea about the homogeneity, and then just calculate your cation ratios, and from the cation ratios you know which stoichiometry type it is, and then you know which defects you will mainly have. This doesn't mean that you don't have the other defects as well, but they will be in much, much less concentrations. So, but the main defects will be there according to the stoichiometry type model.
Yeah, but I think the following question would be just, I still not quite sure. For example, we do a lot of like TEM, cross-section TEM, use the EDS. Actually, we don't do the, we don't do too much on the XRF. We do the EDS, cross-section of the TEM. We usually look at the green interior composition. But I still got the question. We are assuming if, for example, if we confirm, okay, this is the composition of the green interior, right? Yes. And then we corresponding to like what has been characterized from like the powder sample. But my question is, why do the defects formed in the thin film, like when we're modulating the precursor structure, and when we're modulating like the annealing profile, because we know clearly it affects the reaction path. Yes, yes. So why this one will have the same defects with the powder sample, because you mix everything together, right? So because the reaction path is different. So is it I just wonder maybe it is possible when the reaction path is different, the defects might be different. It might not
so when your reaction path is different, then you may get slightly different compositions, and
okay.
And I will show it in. I will go back to my cation ratio plot with the maybe to show you that one. No, the final one. So. For instance, especially if you cross a line, if you cross one of these lines, then your composition will be not so different, but your stoichiometry type will be totally different. So you will have very different defects. Even if you are say, okay, my composition is not so inhomogeneous, but these are dangerous points when you cross the lines. So. If you are between two lines, then your composition can vary a little bit, but you will have the same defect types. But if you cross the line, your composition will vary a bit, but you have different defect types. So maybe this then happens just by chance.
I would say probably in our research community we should do more like a comparison analysis. Yeah. For example, we get like the thin film one, and particularly for the high efficiency one, and then we compare. Yes. So there might be more. I think there might be more knowledge generated just for how the defects formed, so and how we should how the defects yes. I think that's very important.
So we, as I said, we studied also chalcopyrites a lot, also on powder, of course, and then. At conferences we were asked, how could you be sure that in the thin film it's the same? That's why we made also one study, in principle two, about copper indium selenide thin film. So the colleagues at the PV-Combi, they made big thin film for us and they scratched it. And then we measured the scratched thin film as a powder. And we did it for copper indium selenide and for, I think, a sodium doped copper indium selenide, and we found the same defects as in the powders. So that's why we think that the work on powders is comparable with the work on what is the scenario in the thin film.
I think we need to do, or probably similar way we can do the comparison for the powder and the thin film for the kesterite.
Yeah, but I need a homogeneous powder. A homogeneous thin film. Yes.
Because we do a lot of a significant amount of including the cell mapping, right? And EDL's mapping of our film, but still for TEM, I mean, you can only look at the small area. It's impossible to look at the large area, but we are trying as homogeneous as possible. I think we need another try, because for chalcopyrite, I mean, the defects is much less complex compared with kesterite.
Oh, the chalcopyrites are easy.
Easy, yeah, much easier. Yeah.
because there are not so many defects. They can be only copper poor. There is no way to make them copper rich. Only one direction.
Exactly. Yeah. So the second question related to perovskites. You mentioned like for the perovskite, like they are how to say, rotating around, right?
Yes.
So that rotating, when you say, because I just want to double confirm, you said when you replace the iodide with the chloride,
Yes.
the rotating reduced, right?
It gets faster. So the time between the jumps is shorter. So if you have it like the molecule here and this 3 hydrogen, it stays there and then it makes a 120 jump, rotation, and then it stays a while there and then it makes the next one. And if you have the chloride, this time is shorter. So the iodide stays longer with these bonds to the halide. And because when it rotates, the bonds have to be broken, and then it rotates.
Ah, okay. So that means for chloride, because like the frequency actually is faster, right? Actually, basically. So basically, like before they break broken, they already go to the next one. So mean that's like a formation energy, like the bonding.
The bonding is weaker.
It's very strong.
For the iodide, it's stronger.
Very
Yes.
weak. So they can stay there for a bit, because it's sort of like a breaking.
Yes. So for the chloride, they stay not that long, because it's easier to. So the bond is weaker. It was here. So only 135 picosecond, and more than 1,600 in the iodide. So it stays in this bonding, and then it rotates to the next one. And this is just one. This is we studied both, also this C4, and then this. They also can make this. Yes. Yes.
Yeah. So for the iodide, they got this one and this one. All.
It depends on the symmetry.
Yeah.
So if we are tetragonal, it can has both. If we are orthorhombic, I think it has only these ones left over. So this was a tricky data analysis done by my colleague Götz Schuck. He's an expert. That's why I hired him. He's an expert in quants. I'm familiar with quants, but I have never analyzed the data.
But this one is all method powder or single crystal?
This is powder. This is measured on a powder.
Possible on the single crystal?
I would have to think about on a single crystal, maybe. Yes.
Yeah. So we do some single crystal. I guess like we can do more like a comparison, because single crystal so far like they're still like a relatively stable compared with the simple one, and definitely it's because of synthesis method different. So
this also can be measured at ANSTO, so no problem to measure quants at ANSTO.
Okay.
So you don't have to go to the ILL. So
do you know how they make a powder of that?
This is we made the powder from solution.
So similar way to the single crystal one.
You have this GBL, DMF or something mixtures, then you put the binary precursors in, and then it crystallizes. Okay. You have to heat it a little bit up, it evaporates, and then you have,
I got it.
It's very easy.
Yeah, so it's similar to single crystal.
Easy and fast. Much faster than to grow chalcogenide.
Thank you.
I have a follow-up question after Gina. Does that mean for your neutron scattering analysis, if the composition is the same, you believe that the defects should be similar?
Yes.
Okay. No matter in what kind of methods you achieve the material, you think?
As long if it is
homogeneous.
Because these considerations from the off-stoichiometry type model are purely crystallographic considerations. Has nothing to do and chemical. So in which direction you go in the phase diagram. That's why you can calculate it easily from your solid solution formula. And this was the idea from Alain Lafont. And that's why it works for kesterite, for stannite, for Wurtz-kesterite, for Wurtz-stannite. This works. And we measured different. We also measured the copper zinc silicon selenide, which is Wurtz-kesterite. It also shows the copper zinc disorder. It also shows the point defect. It's all the same behavior. Yeah.
Yeah, but the question is that the crystallinity using different method might be not the same.
The crystallinity.
Yeah, I mean.
Yeah.
of
When
course.
we do the,
But the point defect is the same.
that should be the crystalline defects, not the point defects.
Ah, you mean
The green interior.
grain boundaries and so, or you mean
interior quality.
dislocations, something
Yeah,
like
yeah,
that.
yeah,
Oh,
yeah.
this we don't study with diffraction.
Okay.
This is more Daniel Aburas who is looking for that.
It's a point defect. I think like a crystalline defect, like a stacking folds or
Yeah.
Yeah, you
Okay.
don't get that.
No.
Yeah. And the green boundary is another
The next, this is a microstructure.
Yeah, exactly.
Yes.
Yeah. They all matters.
they all matter. Yes, they all matter.
Okay. Do you have other question? If no, let's thank our speaker again.
Thank you.